memorizing. Stop! And here's our warm-up. Don't let me go away. Hang on.
What's can they hear us? Can they hear us?
Yeah? Yeah.
Hello.
Okay. Okay, so quietly looking around the room, it looks like every single group said that the next term in the sequence was 24. Too bad you're all wrong. No, I'm kidding, you're all right. Okay, and then 0.00001. Every single group got that one. Well done. It looks like we're all pretty good at patterns. All right. So then, whoa, someone had some algebra 2 before, or at least exposure to sequences and series. Wow. Okay. So Shreyas and Manav. Did I say Manav or Manav? All right. So where did you learn series? Mr. Jones? Does he teach in CMS? Oh, okay. That's amazing that you remember it. So, well done. Okay, fantastic. Okay, what I was really looking for part C was just like to add 4, right? So, how do you get from one term to the next? You add 4. So, plus 4, add 4, add 4, add 4, add 4, plus 4. Beautiful. Fantastic. Now for the next part, divide by 10, divide by 10, divide by 10. Move the decimal point. That's interesting. Okay. Divide by 10 or just move the decimal point. Times 0.1 times 1/10. All right, divide by 10 and 4. Okay. Look, these are fantastic. So well done with your answers. So this one, you are adding 4 each time. The next term is 24. This one, you are dividing by 10 or multiplying by 1/10 each time. So you get 4 zeros and a 1. For this one, you add 4. And for this one right here, you divide by 10. Or multiply by 1/10. They're both the same thing. So, well done. Fantastic. Good work. Good warm-up. So today is our very first lesson of our very first full unit, which is Chapter 1, Section 1. And if you want to give it a title, you can call it recursion or recursively defined sequences. You can either call it recursion or recursively defined sequences. This is Chapter 1, Section 1, recursion. Are you ready? It's all good. Yeah. Okay. I need to make this bigger. There we go. So you don't have to write anything from the screen. This is just talking about how sequences are strongly associated with patterns and recognizing patterns. You're going to see a lot of patterns in this unit. And it's talking a little bit about how sequences and patterns get used in real life. I'm going to tell you what I love the most about, so sequences go kind of hand in hand with this thing called series, which is just adding the terms of the sequence together. We will not be doing series until later on. There's no series in Chapter 1 at all. So it's all sequences, which are just lists of numbers. And then later on, we'll get into adding them together. But my favorite use for series, now, I took a class last summer called Enumerative Combinatorics, and in that I had made a connection that I had not made before, which was how series apply to probability. probability and statistics, right? Which was kind of cool. It was a connection I hadn't made that was really fun. But the one that I use the most often as a calculus teacher is that on your calculator, and this might not look like your calculator, now I know you guys have probably not done logs yet, but I'm pretty sure in geometry, do you have to do sine, cosine, tangent, some light trig? Okay, so how does your calculator know what the sine of 22.68 is? Like if I type sine of 22.68 and hit enter, it's going to give me an answer. How does it know that answer? It's just it's 3 letters and a number. How does it turn that into an answer? It's not like there's a formula, right? So how does it know? What does it do? Does it have a great big gigantic table built in for every real number in the world? Yes. Yes. So if I did 28.685, that would be on the table. Yep. It's a big table. Yes. Okay. So actually how your calculator computes these values, same thing how your computer computes these values, it does it with a series. There is a series that approximates sine. There's a different series that approximates cosine, and there's a different series that approximates tan, and there's also one for log. All these letter functions, they are all approximated through series, and that's how your calculator gives you numbers. The answers your calculator gives you are never exact. They are always approximations, and they're done using series. Hi. So, like when you tell your calculator how many decimals to round to in the mode, you're actually telling it how far out it needs to go in the series in order to give you an approximation that's that good, right? So, anyway, big application. I digress. So, all right, so we're going to start with a little problem. Simple sequence about tables and seats. So if you look at the square table, and you look at the seats around the table, a square table can sit 4 people. If you take 2 square tables and push them together, you can seat 6 people. If you take 3 square tables and push them together, you can seat 8 people. The first question I want you to ask is how many people can sit at 10 tables pushed together? And then the second question I want you to figure out is how many tables are needed to seat 32 people? So 2 different questions. We'll talk about the other one later. So number 1, how many people can sit around 10 tables pushed together? And number 2, how many tables would be needed to push together in order to seat 32 people? In your groups, I want you to come up with answers. Don't write them on your whiteboards. This is just on paper. I'm going to give you a minute to discuss and see if you can answer both of these questions. Go. Okay, so Isaac, how many people can sit at 10 tables pushed together?
22.
22. Did all groups get 22?
Yes.
All right. How did your group figure out 22? What did you guys do?
So basically, you need 2 people at the end. So basically, you subtract 2, and then you just multiply by like 2s.
Oh, okay. So each table has 2 people, right? Plus the 2 at the ends. Yeah. Okay, that works. That makes sense. All right. Did anyone do anything different? Yeah. Wait. All right. Are you Jose?
Yeah.
Hi, Jose.
We just wrote down the pattern.
You just wrote down the pattern, right? So you just started by there's 4. Oh my gosh! Every time now I'm having to re-click. Oh, I don't want that. There we go. All right. So you did 4, 6, 8, 10, 12, 14. And before I keep going, so just so you know the table number, this is table number 1. This is 2 tables, 3 tables, 4 tables, 5, 6, 7, 8, 9, 10. So you just wrote out the 10 terms, right? Perfect. Fantastic. Any other thoughts? Yeah.
So,
And you're Shreyas.
yeah. So, the first one, there's 4 people at the seat, right?
Yeah.
So, for every other one, you're adding 2 people.
Mm.
So, what we thought was I did 4 added to
Okay.
Multiply that with the difference.
Yeah. Okay. So what Shreyas is saying is you start with 4. That's your first table, right? And then after that, you're adding 2 every time. So if this is table 1 and we're starting with 4, then we're going to add how many 2s to get to table 10? We're going to add 9 2s, right? So you start with 4, and then you add 9 2s, which is 18, and then you land on 22. Right? So different methods. Very nice. All right, 3 different methods, all got the same answer. Well done. All right, so the next question, Tori. Hi, Tori.
Hi.
How are you?
Good.
Good. Tori, how many tables are needed to seat 32 people? It is 15. How did your group get 15? There's 2 ways, actually more than 2 ways.
Okay, so what I did was kind of like what I did. I just subtracted 2 since there would be the 2 people at the end.
Mm-hmm.
And since there was a 30 left, I divided them by 2. So we
Okay.
got 15.
So, and you're, wait. You're Abby?
Yeah.
All right. So, Abby said, hey, look, we have 2 people a table. So if we did 15 tables, that would be 30 people plus the 2 on the ends. That would give us the 32, right? Good. Did anyone do anything different? Nobody just listed off the next 5 terms and got to 32?
Yeah.
Yes, there we go. Okay. There's nothing wrong with that, right? It's a perfectly valid method. It's perfectly mathematically sound, right? All of these are fine. So it's really just to kind of get you used to working with sequences. So there's a number of different ways that you can approach them. One is to just list off all the terms. Listing off all the terms is fine unless you have to list, 200 terms, then it gets a little long, right? So then maybe finding other mathematical methods could go a little faster. All right, good. So we're going to learn a little vocabulary. You don't have to write all these words down. I'm actually going to below here write what I think you might want to learn. Now, so Manav and Shreyas both wrote for part C. They have this thing where it says A sub n, this A and this little n next to it. That is how I was always taught sequences as well when I was growing up, and even all through my years of teaching. This book that we use this year is the first book I've ever seen that doesn't use that notation. For some reason, they've chosen to use U. So we're going to use the letter U. I don't know what the U stands for. It just stands for U. So we're going to use U. But it doesn't matter. Just know that in some books they're going to say A, and in some books they're going to say U. In our book they say U. All right. So here's the thing. You have a letter that's like the name of your sequence, and then you put this little number next to it that's a little bit lower. So U in the past, if I did this, you guys would know this was U squared, right? It's kind of a raised up little number. That's called a superscript. This is called a subscript. So when you have a number that's kind of little and lower down, it's called a subscript. And this U, and so when we say it, we say U sub 1. This has special meaning. This means, whoops, I can write the first term. And when we speak it, we say U sub 1. U sub 1 means U with a subscript of 1. If I wrote U sub 2, what do you think that would mean? The second term. And I would speak it U sub 2. U sub 2. And I could keep going U sub 3, U sub 4, for all the terms in the sequence. But there's also a special term called U sub n. And U sub n is called the general term for the sequence. The general term. You could plug any number in you want for n. So if n was 1, it would be the first term. If n was 2, it would be the second term. So u sub n is the general term. And you say, of course, u sub n. So that's called the general term for the sequence. Now, let's see. So we've talked first term, okay, second term, general term. All right, and now we're going to talk about recursive formulas. So if we have to write a formula for a sequence, and the formula is going to be recursive. A recursive formula is a formula where you write what to do based on the term, the prior term, or the previous term. So when you guys, for part C, when you wrote add 4, that meant go to the term right before it and add 4, right, to get the next term. So the next term is the previous term plus 4. Does that make sense? Okay. That's called recursive. So it means that each term is defined based on the term before it. It's called a recursive sequence because each term, in order to find the next term, you base it on the term that's right before it. Now, we are going to learn how to write some recursive sequences. We're going to start, let's see, like this. I'm going to move these down. All right, so I don't know if you can see this well, but we're going to look at the sequence that we were just talking about. That's our table sequence. So it's 4, 6, 8, 10, 12, and so forth. So for this sequence, what is u sub 1? 4. Very good. That would be your first term. Let's just see if you know what the next term is. What's u sub 2?
6.
6. What's u sub 3?
8.
All right, got that. In general, we have u sub n. Now, how do you write the previous term? It's not like you can write u sub 26. I mean, that's not a specific number. So what we have to do instead is we have to write, we need notation for the previous term. And that notation is u sub n minus 1. And I'll show you why in just a second. So we have u sub n equals u sub n minus 1. What are we adding to go from one term to the next here? Plus 2. Now, u sub n minus 1 in general means the previous term. The previous term. All right, I have so many things like. First, in order to write what's called a recursive formula or a recursive rule, you need 2 things. We're going to do this about 20 times today, so you'll get used to it. You need the first term, and you need the general term. Those 2 things are required in order to write out a sequence. The first term and the general term. Everything else is extra, but you have to have the first term and the general term to be able to write the sequence. Now, is there anyone here that's looking at this notation and you're like, I don't know if I quite get that? Who's going to admit? Nobody ever? Okay, thank you. 1 person in the whole class? Okay. All right, well, thank you for your honesty. Because I have a feeling there's more, but they're just not saying it, right? Okay. What the heck does this u sub n and this u sub n minus 1 mean? Well, let's take a look at this sequence, right? Everyone kind of see that? So this right here, this 12, which term is that? That's u sub 5, right? All right. So if I were to write u sub 5, well, u sub 5 is the same thing as u sub 4 plus 2, right? U sub 5 is 12, u sub 4 is 10, plus 2, right? So u sub 5 equals u sub 4 plus 2. Well, if you let n be 5, that's like the current term you're on, if n is 5, what's n minus 1? 4. So the 5th term is equal to the 4th term plus 2. Does that make sense? So if u sub n means any term, u sub n minus 1 means the term right before it. Because you're taking your term number and going to the one right before it, minus 1. So if it wasn't u sub 5, say it was u sub 35, right? Then the 35th term equals the 34th term plus 2. You could stick any term number in there that you want. Does that help a little bit? It's making sense? All right. Good, good, good. Okay, so let's start with a little example. A concert hall. So you're in a concert hall. If you've ever seen concert halls, they kind of like go, the seats kind of go like that. It's like a kind of a, not quite a triangle, but kind of. So the concert hall has 59 seats in row 1, 63 seats in row 2, 67 seats in row 3, and so on. The concert hall has 35 rows of seats. Write a recursive formula to find the number of seats in each row. How many seats are in row 4? Which row has 95 seats? The first thing that we're going to do is write the recursive formula. When you write a recursive formula, you have to give me 2 things. You have to give me the first term and the general term. We're going to do the first term together. What is u sub 1? 59. Does everyone understand why u sub 1 is 59? Because that's how many seats are in row 1, right? Your job as a group is to take the next 30 seconds and see if you can write a general term for the sequence. Go. How you doing? Did I say your name right? Okay. So what did your group get for u sub n?
Yes. Sorry.
That's okay.
U sub n.
Beautiful. Every time. I don't know how I'm going to get it to stop doing that every time. Okay. So u sub n minus 1 plus 4. Is that what every group got? If I ask you for the recursive rule or the recursive formula, it has to have both of these. It can't just have this. Why can't it just have this? Let's pretend that I didn't give you that. And I said, all right, this is my rule for my sequence. Tell me the terms. What's first term? You have no idea, right? You have no idea where to start. You have no idea what the terms are. All you know is that each term is the previous term plus 4. But if you don't know where to start, you can't write the sequence. So you have to give me both the first term and the general term as your rule for the sequence. You got to have both. All right? Okay. So how many seats are in row 4? This one, it's a pretty low number. You could have just written out the first 4 terms, right? 59, 63, 67, 71. Good movement. All right, 71 seats are in row 4. Did everyone get 71? Okay. So now we need to know which row has 95 seats. It wouldn't be terribly hard to just keep writing terms until you get to 95, right? And see which row you're at. That's fine. Are there any other methods? I didn't do anything different for figuring out which row has 95. Yes,
You are Anthony. Are you Anthony?
Yeah.
Okay, good.
So, I know like Shreyas and Manat talked about it, the formula right there.
Uh-huh.
So I essentially used that formula and plugged it in backwards. So instead of trying to solve for A of n, I instead solved for n and just plugged in A of n, which was 95.
Okay.
And solved backwards.
All right. So we have some students who have really good memories and have remembered that formula, which is called the explicit rule for an arithmetic sequence. We haven't gotten there yet, but if you want to use it, it's certainly mathematically correct, and you did great. So well done. Okay. All right. If you don't remember, how many of you honestly just don't remember that? Okay. All right. So we need another way, but that one's fine. So either you list out the terms, or you can. Oh, yes.
So if the first term is 0, I do have to write out the
Yes.
Okay.
Yes, that's a very good question. The question was, if the first term is 0, do I still have to write use of 1 equals 0? Yes, you got to have a starting point, right? Okay, so the question is, which row has 95 seats? Well, I could say 59 plus what, right, equals 95. Well, it's something where I'm going up by 4s, right? So let's see, 4 times something. So if I do 95 minus 59, well, let's see, 95 minus 60, 35, 36. All right, so that means there are 36 more seats in this row than there are in the first row, right? So if there's 36 more seats in this row than there are in the first row, and I'm adding 4 seats to each row, that means that this row has to be 9 rows back from the first row. Does that make sense? I took my first row, I added 9 4s to it, and I got to the row with 95 seats. So which row is it? It's the 10th row. So I started, this is my row 1. I started with row 1. I added 9 rows. So I end up at row 10. You got the row 10. Again, you could just list out the terms. Yeah, that's okay. Listing out the terms is fine. You can just think about it. You can use an explicit formula if you remember it. We aren't going to get to, we will get to explicit, just not yet. All right. Good. There are 2 types of sequences that we are going to study. There's more than 2 types of sequences, but there's only 2 that we're going to study in this class. So the 2 we're going to study are arithmetic and geometric. In your groups, I want you to look at these 2 sequences, take a minute and see if you can decide what makes an arithmetic sequence arithmetic and what makes a geometric sequence geometric. What's the difference between the 2? Do y'all have a decision? All right. Mary, how are you? Good. Mary, did your group decide what makes a sequence arithmetic? How do you go from one term to the next? You add. Does everyone agree? All right. So with arithmetic sequences, you're going to add or subtract. Really, we always call it adding. You either add a positive or add a negative, but you can think add or subtract. And then geometric. How do you go from one term? Let's see, wait. Alyssa, how do you go from one term to the next in a geometric sequence? Yes, very good. You either multiply or divide. We're always going to say multiply, but that's okay. Okay, multiply or divide. All right, so whenever you add or subtract to go from one term to the next, you're on an arithmetic sequence. When you're multiplying or dividing, you're on a geometric sequence. All right. before we move on, how do you know what number you're adding? Like, what number are we adding each time? 2. How did you know that? Find the difference between any 2 terms, right? Take any term and subtract the term before it. And that's the number you're adding each time. All right. What about here? What am I multiplying by each time? 2. I'm multiplying by 2. How did you know? You can take any term and divide it by the term before it. And then you figure out what you multiply by. All right, we'll do practice. So, an arithmetic sequence is one with something called the common difference. The common difference. And so here's our general term for an arithmetic sequence. So u sub n equals u sub n minus 1 plus d. D is called the common difference. And this is an arithmetic. D is called the common difference. How do you find the common difference? Just take any term and subtract the term before it. If you look at the graph of an arithmetic sequence, this is actually the graph of our concert hall question. And we aren't going to be graphing sequences today, but you will be. When you're graphing sequences is actually kind of fun because all you have to do is plot points. It's literally plotting points. So you never connect the dots. So when you're talking about a sequence, they are distinct number. It's a distinct list of numbers. The first term, the second term, the third term. It's not like there's a whole bunch of stuff in between. I don't know if you guys know the words. You know the words domain and range, right? Okay. Domain is your input. So your input for a sequence are only integers. The number 1, 2, 3, 4, 5. Your domain is just your counting numbers. First, second term, third term, fourth term, fifth term. Your domain is just the term numbers. Your range, your output, those are the actual values of the terms. 59 seats, 63 seats, 67 seats, and you just keep going from there, right? So our first term, 59. Second term, 63. Third term, 67. It's just a set of points, like individually graphed. So when you're graphing a sequence, it's literally just plotting points. This sequence is arithmetic. If we were to connect the dots, what shape would it make? It'd be a line, be a straight line, right? All right, does everyone kind of see that? Can you visualize that's a line? Good. All right. That's all I need from this page. That's all you have to write. Okay, now we're going to talk geometric. How many of you in geometry or honors geometry studied fractals? Oh, fractals are so cool. Did you study fractals? Basically, yeah. A fractal is like the more you zoom in, the more detailed it gets. So, yes?
But if you had a fractal in real life, it wouldn't work because the atoms can only be so small.
Right. Yeah, fractals are more theoretical. Although, there are some beautiful real-life examples of fractals. I'm trying to think of the one that I can't think of it in my head right now. I always want to go to the snowflake, but that's not the real-life example I'm thinking of. I'm thinking of, it has to do with probabilities. I'll have to look. It's the one with the beautiful coloring and shading. Anyway, but right now we're going to talk about the Sierpinski triangle. So all this is you're just constantly subdividing your triangle. So it looks like one triangle with a bunch of subdivisions, but really what we're doing is we're counting the individual red triangles in each figure. So with the Sierpinski triangle, stage 1 would be your use of 1. How many red triangles do you see? 3. Now let's just list off, just for the heck of it, how many triangles are there in stage 2? Oh, count again. Do you see 9? Okay, there are 9. Take a guess without counting. How many are there in stage 3? There are 27. So what you figured out there is what you have to multiply to get from one term to the next. What do you have to multiply by? 3. You have to multiply by 3, right? 3 times 3 is 9, times 3 is 27. You're multiplying by 3 each time. Before we move on, I want you first to give me a use of n for this sequence. Give me a general term for this sequence. Use of n equals use of n
minus
minus 1
times
three. Yeah. So it's use of n minus 1 times 3. Now, personally, I like to put my numbers before my variables, so I would write 3 use of n minus 1. Each term is the previous term times 3. Each term is the previous term times 3. All right, here's what I want you to do in your groups. I am going to give you a minute to figure out how many triangles are in the 20th stage of the Sierpinski triangle. Once you figure it out, I want you to send one member up to your whiteboard to write the answer. All right? You don't have to give me any work, just the answer. Okay. Am I on board? Nope. I gotta click. All right. So several groups gave me the answer of 57, and then a minute went by, and then they ran up and changed it. Because either someone within their group or outside of their group convinced them that the 57 was wrong. Are you sure the 57 was wrong?
Yes.
So correct.
So correct. Why was the 57 incorrect? Why is the 57 wrong? It's too small?
It's close.
It's close? It is close, because the correct answer is only 3.5 billion, right? All right. Yeah, so it just depends on how you define close, right? Okay. All right. So, all right, if we list off the first few, oops, that's a 3. 9, 27, we're timesing by 3. What's the next term? 81. 243. You're already beyond 57 at the fourth term, right? Okay, so you know it's not 57. You keep going. So 1, 2, 3, 4. We're 5 terms in, and we're only at 243. How is 243 is not that big compared to 3.5 billion, right? If I make $243 this weekend, or I make $3.5 billion this weekend, there's a little difference, right? How on earth do we go from this all the way to 3.5 billion in just 15 more terms? That's the beauty of geometric sequences. Arithmetic, you're adding the same amount each time. So you're just growing same amount every time, and that's how you get to 57, right? Is you treat it as an arithmetic. That's the 57. So geometric, you're multiplying by 3 every time. When you follow a geometric series or sequence, when you follow a geometric sequence, you start to grow, right? And then all of a sudden, I kind of think of it as turning a corner. It's really not a corner, but it kind of visually feels like it. And all of a sudden, the numbers just go, and they just skyrocket up, right? Now, what in real life follows a similar pattern? Population follows a similar pattern. Someone else said it. What's in the back? Money. Absolutely. Which is why, okay, here's a real life lesson. We're going to get into this more when we get to exponential growth, which is why you should start saving for retirement the moment you get your first job, right? I mean, at least the first year out of college. But the second you can start socking money away, you should, because if you wait until you're in your 40s, like a lot of people do, your money never has that chance to turn the corner. And if you start when you're young, your money gets to that corner. Maybe like by the time you don't think it, like you're like, gosh, she said it was going to like skyrocket up, and it hasn't yet. That's because it usually takes a number of years. You might not be, until you're in your 40s or so, and then all of a sudden, whew, right? And then it'll start like really growing big. And so that's what happens. That's why you want to start early. You get these all out of the way So by the time you retire, you're a millionaire, right? Or billionaire, depending on, right? Okay. So anyway, all right. Yeah, so that's it. So just so you know, just so for notes, state u sub 20 was your first term, and then you had to multiply times 3 19 more times. Now I saw one group who just did 3 to the 19th, but they forgot to multiply it by that initial first term. So you have 3 times 19 more 3's, basically. So you end up with 3 to the 20th. Now, normally it wouldn't be 3 to the 20th, like if this is just because the first term happened to be 3. But if the first term was 5, it'd be 5 times 3 to the 19th. Anyway, so you end up with 3, 4, I'm just going to copy, 8, 6, 7, 8, 4, 4, 0, 1. Okay. All right, well done. Good work on that. All right. Okay, so don't write all these words down. Just know that when you have a geometric sequence, the number you're multiplying by is called the common ratio. That's what you multiply to get from one term to the next. And your general form looks like this. So it's u sub n equals r times u sub n minus 1. It's each term equals the prior term times the common ratio, which we call r for ratio. This is the general form for a geometric sequence. General term of a geometric sequence. So u sub n equals r times u sub n minus 1. Now, if you like to look at the notes, this right here, this funky u sub n over u sub n minus 1, they're telling you how to find r. If you want to find r, it's just any term divided by the term before it. All right, does everyone have these things written down somewhere? Yes? No? Yes? I'm going to learn some names. Let's see. Ingrid. Hi. How are you? Good. Okay. Do you have this written down? Okay. All right. A couple of quick examples. So the first one, let's just write the first 5 terms. If u sub 1 is negative 3 and u sub n equals u sub n minus 1 plus 4, where n is greater than or equal to 2. Now that where n is greater than or equal to 2, don't let that freak you out. All that's saying is, this is our first term. For any term starting with the second term, n greater than or equal to 2, so starting with u sub 2, u sub 3, u sub 4, right? So any term starting with the second term, you follow this pattern. So the first term here, and then all the remaining terms, you use this guy. That's all that means. You don't have to, when you guys write your sequences, you don't have to write this part. That's okay. You can just write this part. So first one, just write the first 5 terms done on paper. Second one, I want you to find the rule. I want you to write the rule for this sequence. All right, so take a minute. You're going to have to determine if they are arithmetic or geometric or one of each. Yeah, I'm going to pause the video. Cut to learn names. All right. Sophia. Hi. How are you doing? Are you? Good. Sophia, can you tell me the first 5 terms of this sequence right here? The rest of you, quiet down. Quiet down. Hang on. I'm sorry. Quiet down so I can hear Sophia. All right. One more time. I'm ready. Beautiful. How did you get those? You add 4 to each term. Any questions on that one? Did you all record? What kind of a sequence is this? Arithmetic. Arithmetic you add. right? A's go together. Arithmetic, you add. Okay. All right. This next one, so I need a rule. I don't need the first 5 terms. I need a rule. There are 2 things required for a rule. Luke, how are you? You good? Good. The first thing that's required is for you to just tell me the first term. I'm ready. What's the first term? 12. If you don't have that, you're not going to get credit for your sequence. Right? You got to have both. Got to have both. All right. So before I ask you for the general term, did your group decide that this was arithmetic or geometric?
Geometric.
Geometric. Well done. Okay, but back to Luke. All right. So Luke, did you figure out what number you have to multiply by to go from one term to the next? 1.5 is correct. So your general term is u sub n equals 1.5 times. You got it. Beautiful. Well done. Now, 1.5 could also be written as what? 3 halves. 3 halves, right? Now, how did they find the 3 halves or the 1.5? Just take any term and divide it by the term before it. 18 over 12, right? So if you do the second term divided by the first term, you get, it just reduces to 3 halves. And that's your common ratio. Does that make sense? All right, good. So for this one, I want you to first go ahead and just take a minute, copy this down, figure out u sub 1, u sub 7, and u sub n, and then write the recursive rule. And I'm just going to take a peek. Yeah. I want the recursive rule on your whiteboards. Send a different student up. All right. Actually, you know what? Let's hold off on this. Let's just do this one on paper, and I'm going to do the next 3 on your whiteboard. So let's do this on paper. I'll give you about a minute or so to figure out u sub 1, u sub.
If it's adding or subtracting, then it's
All right. What is? Wait. I'm going to call on somebody. Get ready. Have u sub 1 in your head when I call on you. Omar. Hi, Omar. How are you? Good. What's u sub 1? Negative 9.2. Now, this is term 1, 2, 3, 4, 5. Wow, they gave us a lot of terms. They asked us for u sub 7. First of all, Omar, was this arithmetic or geometric? Arithmetic, but there's decimals. That makes it geometric? Decimals?
No, because you're adding this.
I'm just messing with you. You're right. Okay. Yeah, it's arithmetic. What are you adding each time?
3.1.
3.1 is correct. So if this is term 6, what's term 7? 9.4. You take term 6 plus your common difference, which is 3.1, and you get 9.4, right? Okay. So, and then you need a u sub n. So what is u sub n equal?
U sub n minus 1
Plus 3.1. Beautiful. All right. So the rule, Grace, right?
Yes.
Hi, Grace. All right. Good. All right, Grace.
Yes.
The rule is already on the board. You just have to tell me the right pieces to write. It's already on the board. What do I write first for a rule? What is u sub 1 equal? She's got this. She can do this, right? Okay. And then Grace. What's the other part I need for the rule? Let her do this. Let her, give her a chance to shine, right? Okay.
No.
Okay.
U sub n minus 1 plus 3.1.
plus 3.1. That was beautiful. Well done, right? Okay, do you all have both of these down for your rule?
Yeah.
Yes? All right, good. All right, so last thing, let's just make sure you've got it. There are 3 sequences on the board. Those of you who wrote the answer for that last problem, the one with the billions on it, the triangle problem, you guys do not go up. So everybody else, let's label these. I'm going to call this A, B, and C. I want a rule on the board for each of these. Go ahead and go. You can each pick one, however you want to divvy it up. Just for the video, because every single group got it correct. Someday, I will remember. All right, so u sub 1 equals 3, u sub n equals 4 times u sub n minus 1. This was a geometric. U sub 1 equals -7. U sub n equals u sub n minus 1 plus 4. This was an arithmetic. And the last one, was it arithmetic or geometric? Geometric. U sub 1 is 1/44. U sub n is 1/12. U sub n minus 1. Or I had one group who put 0.083 U sub n minus 1, and that was fine. All right. Okay. Closing question. So very quickly, this was from our opener, the warm-up. The first sequence we did in the warm-up, 4, 8, 12, 16, 20. You had to name the next term. Tell me anything about this sequence right now.
U sub 1 is 4.
U sub 1 is 4.
U sub n is 0 minus 1.
Very good. U sub n is u sub n minus 1 plus 4. What kind of sequence is it? It's arithmetic. What's the common difference?
4.
4. Good. Okay, second sequence. What kind of a sequence is it?
Geometric.
Geometric. What's the common ratio? 1/10. 1/10. It's what you have to multiply by. So common ratio is 1/10. What's u sub 1? What's u sub n?
U sub n is
1/10. Yes! Beautiful. 1/10 times u sub n minus 1. Fantastic. All right.